So now that we sort of have this sense for how implicit differentiation works, I really want to, in this lesson, talk about one of the neat ways that we can use implicit differentiation to effectively find derivatives of things that are either hard to take the derivative of or that we literally don't know how to take the derivative of. So we're going to be getting into that and sort of how to leverage implicit differentiation to our benefit. So let's go and take a deep breath before we get started. And let's begin. So I first want us to sort of recall and remember, what we learned when we first learned implicit differentiation. And the main idea, like I tried to sort of capture the idea that the whole lesson in one sentence is that any time that we take the derivative of a variable that isn't our variable of differentiation, we have to use the chain rule. Okay, so for this example, find an expression for dp dt, given that p equals t squared minus 4 root t plus 5. Based on what you see in the question, what is the variable of differentiation? Right? And hopefully you're recognizing we can always tell what the variable of differentiation is by looking at the denominator. So in this particular problem, that's t. So anything in the problem, any variable in the problem that isn't listed as a constant or that isn't t, we need to use the chain rule on. We're going to need to write down the derivative of that thing. So this one should be fairly easy, should be, in fact, easier than the ones that we did in the previous lesson. Go ahead and take a moment to find dp dt for this given function. All right, so in this case, I've actually already got p as an explicit function of t. So when I go to take the derivative of this, the derivative of p, well, the derivative of p isn't 1, or we could say that it's 1, but we then have to use the chain rule. We have to multiply by the derivative of that with respect to t. So we're going to get dp dt, make that a little bit prettier, dp dt equals, now each of these things on this side is just in terms of t, so I'm not going to need to use a special chain rule for these, right? I'm just going to get 2t minus, now this is 4t to the 1/2, so we're going to bring the half down and then subtract 1 from it. So this is going to be 2t to the negative 1/2, and then plus 0. As the 5 is just going to vanish as a derivative. So I could either leave my answer like that, or I could write it like this. Either one of these things would be acceptable, and that's that. Yay. The thing I really wanted to get across here is reminding you that the variable of differentiation is the variable that's in the denominator of the derivative expression that they're asking for. In this next example, we're asked to find dv dt, given that v squared is v times t squared minus 4a. Now the problem doesn't say anything about any of these things being constants. As far as we know, all of these things are variables. So, I mean, as we look at variables, I've got v, I've got t, and I've got a. Which of these is the variable of differentiation? Remember, we can always tell that by looking at the variable that's down here. So anytime I need to take the derivative of something that isn't t, I'm going to need to use the chain rule. So this one is not difficult. I made the functions themselves fairly straightforward, but you are going to have to take some care. If you're feeling up to it, I would encourage you to pause the video, work through finding this derivative on your own, and then check back in with me. So when I go to take the derivative of this, the left-hand side, the derivative of v squared, well, anything squared is supposed to be 2 times that thing. But then because that thing isn't t, I'm going to need to multiply by the derivative of what was inside. So the derivative of v is dv dt, okay, equals, now on the right-hand side, I've got vt squared. That's going to be a product rule, right? So the derivative of the first thing, that's dv dt, times leave the second thing alone, plus leave the first thing alone, times the derivative of the second thing. Well, the second thing is t, so I don't need a chain rule. I can just write 2t. Now minus 4 times a, again, a is not t, so this is going to be 4 times the derivative of a, which is dA dt. Okay? Now the question had asked me to find dv dt, so that means that I'd like to go through and I'd like to isolate these dv dt's. So to do that, I want to move this dv dt over, and all of this other stuff I'm just going to leave over here on this side. Okay? So when I move this thing over, I'm actually going to do two things at the same time here. I've got dv dt times 2v minus t squared. So all I really did was subtracted this thing over and then at the same time factored out the dv dt. So I've got this. So this equals this other, green highlighted stuff that I had put over here. 2vt minus 4 dA dt. Okay? Last thing I needed to do, they wanted an expression for dv dt. So great, it's going to be all of this stuff that was on this side, all of that divided by 2v minus t squared. This may not make any sense to us right now, but this is the derivative. One of the things that we're going to be getting into soon as we talk about these things is we are going to start talking about velocity and acceleration and time, and we're going to be making some of those connections. So to be honest, what I'm doing here is sort of front-loading some of this mechanical skill, this practice with implicit differentiation, so ready for it when we get to kinematics. If you have any questions about what's been done here, please make sure that you write those in your notes and that you make a point to either ask me about them like in person or via a message or even by writing them as a question in your notes and circling it so I can make sure that I make a comment when I see your notes. But let's go ahead and see how we can use implicit differentiation to really get some neat results. All right, so if you've been following along so far, and if you're even open to learning about trig, I think you're really going to find this next thing exciting. So the key point that I want to share with us here is sometimes you're going to be asked for the derivative of some function that's either complicated or maybe that you don't even know a rule for, okay? And I want to point out to you that you are totally allowed to manipulate an equation before taking a derivative. You can simplify something before you take a derivative. You can do sort of algebra and arithmetic manipulation before taking a derivative to make something nicer. And now that we have implicit differentiation, we can do even more stuff like that. So let's go ahead and look at this example together. By considering the function y equals arc sine x, pause for a moment, we don't know how to take the derivative of arc sine x. It's not something we've learned how to do yet. By considering the function y equals arc sine x, find dy dx, and hence prove that the derivative of arc sine x is this thing, 1 over the square root of 1 minus x squared. This may seem really daunting, but this problem is going to be really neat. It's going to be a connection of trig and of implicit differentiation and also of trig identities. We're going to bring all of this stuff together in the field of calculus to show us this really neat result. So let's take a deep breath. And let's take a look at this, right? So what I'm thinking here is I don't know how to take the derivative of arc sine. I know how to take the derivative of sine, but arc sine not really. So then what I start thinking is, well, wait a minute. If I were to take the sine of both sides of this, I'd have sine y equals the sine of the arc sine of x. But the thing about sine and arc sine is that they're inverses of one another. These things are effectively going to cancel one another out, and I'm going to get that sine y equals x. Now, it's really important that you recognize this equation and this equation are like identical to one another. So when they say find dy dx of this, I can just as easily find I guess I shouldn't say just as easily, I should say I could even more simply find dy dx using this version of the equation than using this version of the equation. So let's go ahead and find dy dx here, right? This should be a really easy implicit differentiation thing. To find dy dx, the variable of differentiation is x. So the derivative of the left-hand side, derivative of sine y is going to be cosine, leave the inside alone, times chain rule, the derivative of what's inside, that's dy dx, equals 1, because the derivative of x is just 1. Now the problem asked me to find dy dx. So to find dy dx, I'm just going to divide that cosine over. So I'm going to get dy dx is 1 over cosine y. And you might notice that this thing that I got here is not exactly the thing that they wanted me to show. Like, this thing apparently is the derivative of arc sine x, but that's weird. This said arc sine x. It feels like I should be using the same variable here. Man, if only there was like some way that I could like connect this back to something else that I know, right? Well, here's where this gets exciting. Remember that cosine squared x plus sine squared x, and actually let's not make those x's, let's make those y's. Cosine squared y plus sine squared y equals 1. right? Man, if only there was a way I could get just cosine here. Well, couldn't I say that cosine squared y equals 1 minus a sine squared y? And then I could square root both sides and get that cosine squared y is the square root of 1 minus sine squared y. And now I'm at the really exciting part. Did we ever see anything earlier that was sine y? Wasn't sine y x? So isn't cosine y, oops, just realized this shouldn't have a squared here. Isn't cosine y equal to the square root of 1 minus x squared? So that would mean that dy dx is 1 over the square root of 1 minus x squared. Sure enough, that is what we were asked to show. Now, I'm not going to say that this is an easy process, but once we've done it a few times, we kind of get the hang of it. I'd really like you to look over this and make sure that you've made sense of it. I'm actually going to sort of ask you to do this on your own and to try and work through this in a way that you can in this next problem. So make sure that you've sort of looked at this one and you made sense of it. If we go back through the steps again, the idea was we take our original function and we take the sine of both sides, or whatever we need to cancel out the, the arcsine, arccosine, arctangent, so that we get this. We use implicit differentiation to take the derivative, right? Then we step to the side and use an identity to replace what's here with what I originally had, and then I use that to change it back into the original variable, right? So it's definitely a process. If you've got questions or there's something that you're worried about here, make sure that you write those in your notes or you make space to ask me about them. But let's go ahead and move in and try another example of this. So this example is going to run really similar to the last one. It's going to be a little bit stranger, though, because it's going to use an identity that you're not quite as familiar with, or you may not have even seen. As a hint here, I'm going to encourage you to note that there's a similar identity, secant squared x, which is tangent squared x plus 1. If you want to see where that comes from, I'll make a quick note of it over here. We should all know and remember that sine squared x plus cosine squared x equals 1. But because this is true, it means I could divide both sides of this thing by whatever I want. For instance, I could divide by cosine squared x. If I divided all of these things by cosine squared x, what I wind up with is sine squared over cosine squared, that's tangent squared x, plus 1 equals secant squared x, which is sure enough exactly what we have there. So you're going to need to use this sort of fact, this trig identity at some point in this problem. So if you're feeling up to trying this one on your own, go for it. If you want to try just the first few steps, that's fine too. So let's see what we've got here. We want to try and find the derivative of arctangent of x, and we want to start by letting y equal arctan x. So I'll start y equals arctan x. Okay. I don't know how to take the derivative of this, but I do know how to take the derivative of tangent. So I'm going to take the tangent of both sides. I'm going to say that tangent y equals the tangent of the arctangent. Those are going to cancel. Tangent y is basically just going to equal x. Okay. Now that I've got it in this form, I'm going to take the derivative with respect to x, right? So I'm going to take this thing and I'm going to do the derivative with respect to x. So on the left side, the derivative of tangent y, derivative of tangent of anything, is secant squared y times, chain rule, times dy dx. Remember, dy dx is effectively what we want. We want to find the derivative of arctangent. So I've got secant squared y times dy dx equals the derivative of x. Well, that's just 1. Okay. Now, I wanted to solve for dy dx, so I'm going to say dy dx is 1 over secant squared y. Okay. Now, if only I had some kind of an identity for secant squared y. Well, hey, would you look at that? We know that secant squared x is tangent squared x plus 1, so if I just change those x's into y's, as long as I'm using the same thing for both of them, the same argument, whatever I want, it's valid, right? So this means that dy dx is 1 over tangent squared y plus 1. But we recall from before, the tangent of y is x. That means that dy dx, the thing I wanted to find, is 1 over x squared plus 1. This is the derivative of arctangent. Okay. Now, again, it's important that you guys be able to prove these things. You do need to be able to show where they came from, but the good news is you don't need to have them super strictly memorized because they will be provided for you on the exam. So here's where we sort of get to this weird spot where the more things that you have memorized, the better. It's good to know that for the IB exam, in general, when you're doing math in the real world, you're not expected to memorize everything. What you're expected to do is to be able to find those things you need and then be able to use them when you find them. Okay, so there are these three derivatives that we now know or we can find, right? We effectively at this point know or can show that the derivative of arc sine is this, 1 over the square root of 1 minus x squared. The derivative of arc cosine is this, negative 1 over the square root of 1 minus x squared. And finally, that the derivative of arctan is 1 over 1 plus x squared. Okay. Again, these are in the formula book. You can look them up on the exam. You have access to them on the internet. So we know these things. The question is, can we use them? Okay. So I want us to sort of practice that here, right? This question is now asking us, use the appropriate formula from above to find the derivative of this thing. We want the derivative of 4 times arc cosine x cubed. Okay. Do we have a rule for arc cosine? Yeah, we sure do. It's right here. If I want to do arc cosine of x cubed, what rule do I have to use because there's something inside of the arc cosine? Hopefully you recognize that that's the chain rule, right? There's an x cubed plugged into this thing, so I'm going to do whatever this derivative is. I'm going to leave the x cubed alone, and then I'm going to have to multiply by the derivative of what was inside there. So let's try this out, right? What is the derivative? Well, so there's a 4. Okay, let's start with that, right? It's a constant, so I'm just going to leave the 4. So 4 times, now what's the derivative of the arc cosine of something? The derivative of arc cosine of something is supposed to be negative 1 over the square root of 1 minus leave the inside alone squared times, chain rule, that thing that I left alone, the derivative of that is 3x squared. Okay, it's really important. You don't like square this and make it x to the 6th and go, oh yeah, there was an x to the 6th inside. No, the thing that was inside was an x cubed. That's the thing that the chain rule is multiplying the derivative of for us. Okay. Last thing for us to do here is to pretty this up a little bit. Right? I'm going to put the 4 on the top and I'm going to put the 3x squared on the top. There's already a negative 1 up there. So this is going to be negative 12x squared over the square root of 1 minus x to the 6th. And there it is. Okay. I found the derivative of something that involved arc cosine. Okay. And I didn't do it by memorizing those things. I did it by recognizing that I was given those rules. I just need to be able to use them. Now, it turns out in the same way that we were able to find these neat rules for inverse trig functions, we can also find them for logarithms and for exponential functions that we didn't know how to do before. So it's going to be a really, really similar process to what we used earlier to find rules for the derivatives of trigonometric functions. We're going to use those now to sort of look at and make sense of what if I had a non-natural logarithm, an unnatural logarithm, or what if I had an exponential function whose base wasn't e? Okay, so let's go ahead and go through an example of that now. So suppose you were asked to prove that the derivative of a to the x is the natural log of a times a to the x for any positive constant a. So in this case, a is a constant. So you don't need to do a chain rule on a because a is going to be a constant. But if someone were to ask us to take the derivative of y equals a to the x, our first thought might be, I don't know what a to the x is. I mean, I know what e to the x. I know the derivative of e to the x, but I don't know a to the x. So what we would want to do here is we would want to do something. We would want to manipulate this. I'd want to do something to both sides to make this problem better, right? And I'm actually thinking logarithms, right? What if I took the natural log of both sides? What if I said, hey, if this is true, then it should be true that the natural log of y equals the natural log of a to the x. Now, why would I want to do that? In what way does that make this side over here easier? Hopefully you realize, well, wait a minute, if I took the natural log, I could bring that x down, right? When I do that, I'd have the natural log of y equals x times the natural log of a. Now remember, natural log of a is just a fancy constant. And now at this point right here, if I decided to take the derivative in terms of x, what I'd have on the left here, the derivative of natural log y, again, remember implicit differentiation. I'm taking the derivative of something that isn't x. I'd get 1 over y, chain rule, times dy dx, equals, now what about over here? This is actually really simple. This is just a constant times x. The derivative of 5x is 5, 7x is 7, 15x is 15. The derivative of constant times x is just that constant. So if I wanted to find dy dx, I'd just have y times the natural log of a. Man, if only I knew what y was. If only I had some way to like replace that y. Hey, would you look at that? Y is actually just a to the x. And there it is. The derivative of a to the x is the natural log of a times a to the x. Okay? It actually kind of puts things in a different context. If somebody said, hey, what's the derivative of e to the x? I suppose technically the answer is e to the x times the natural log of e. But the natural log of e is just 1. That's why the derivative of e to the x is just e to the x, but the derivative of a to the x is going to be a to the x times the natural log of a. Now, a quick bit of good news for you. Once again, IB Formula Book to the rescue. In case you have trouble memorizing these, or if you're not able to commit them to memory, they're provided for you in the formula booklet. The IB Formula Booklet will tell you, and if you forget 2 years from now and you need to do a calculus problem, or you're taking another calculus course in college, or something else somewhere, you can look up and find, hey, the derivative of the log base a of x is 1 over x times the natural log of a on the bottom. The derivative of a to the x is the natural log of a times a to the x. These are provided for you in the formula booklet. You can look them up on the internet. Okay. I want to do a similar thing here where we practice using these rules, looking at them, seeing them, and seeing if we can use that rule to take this derivative. Okay. We're being asked to do the derivative of x cubed times the log base 4 of the square root of x. Now, before we start this, what rules do you recognize that you're going to need to use here? There's 2 rules. Well, I mean 3 if you count the fact you're going to need to use one of these. Hopefully you recognize that there's a product in here. There's an x cubed and there's a log base 4. And there's also going to be a chain rule here because the thing that's plugged inside isn't just x. It's a square root of x. Okay. So if you're feeling up to trying this, do it on your own. If your brain is tired at this point, you can follow me through it, but I would encourage you to take a deep breath and at least give it a shot, right? So let's see here. If I wanted to take the derivative of this, if I wanted to find dy dx, let's see here, product rule, I'd have to do the derivative of the first thing. Well, fortunately, that's just, this is in terms of x, that's easy. 3x squared, and the second part's easy too, because I just get to leave this part alone, haha. That's the first part of the product rule. Plus, now the second part of the product rule, I leave this alone, and then I have to do this derivative. And it may be helpful for you to actually pull that aside and do this separately. Like over on the side of your paper, how am I supposed to do the log base 4 of something? Well, it says up here that the log base a of something is supposed to be 1 over the thing that was inside. Okay, well, the thing that was inside was the square root of x times the natural log of a, so that would be times the natural log of 4. But then chain rule. We remember we needed a chain rule, so times the derivative of whatever was inside, the derivative of the square root of x, that's basically 1 over 2 root x. In other words, these root x's are going to come together. I'm basically going to get 1 over 2x natural log 4. And so I can bring that here, times 1 over 2x natural log 4. Okay? The only thing I can see here that I could do if I wanted to simplify this just a little bit is there's sort of an x here and an x here, and I could cancel one of those out. So I suppose if I wanted to just go one last step here, I could say that dy dx, the derivative of this monstrosity, 3x squared log base 4 of the square root of x plus x squared over 2 natural log 4. This is definitely messy, but this is something that we can do. And so one of the skills that we're getting into here now is if you forget a specific derivative, we want to remember that we can look it up and that we can be careful in using these rules that are provided to allow us to get through a problem. As always, I hope all of that made sense. If you have any questions, please take the time to email me about them or to write the question and circle it in your notes, and I'll do my best to comment on those and get back to you about them. I wish you best of luck as you work through these problems in practice.